started. This contrast, good for you guys? I wish it was a little tough. A little small.
Maybe add a white border to the letters. Like white border to the letters, maybe. Just change the font. That can help.
Oh. Oh yeah, like this right here. Well, I mean, okay, you guys are gonna have this, so you guys are gonna get that. But yeah, I was just like worried about the contracts in general. But okay, so here's the schedule of the class. Okay, and I circled one. So we're actually in lecture 2. So so the TA, my grad student gave lecture 1, right? And he's supposed to cover like pages 518 through 530. Okay, that's like your introduction to op-amp. So we're going to continue that today. Okay, but a few things I want you guys to know here. So when you guys get this, so here's the lecture number. Okay, here's the date. The different kind of topics that we're going to cover. For example, it has like the chapter, the topic, and the page numbers if you guys want to read ahead, or if you want to go back and read. These areas right here are the dates of the exam, and they're tentative. You know, we may have to change depending on if you have another exam in a class that conflicts with this exam, then we'll change it. You know, I'm pretty flexible. But for example, exam 1 covers lectures 1 through 11. So it's like from here to here. So, you know, you have a couple of days here, well, a few days, because it's just Monday, Wednesday, and Friday here before the actual exam. So it could be any time during this week, but it'll just cover material from last Friday. And same with all the other exams. Okay. What else do I want to say about this? Oh, this area right here is like our Thanksgiving break. Okay. And of course we have no class on these days right here. Labor Day, fall break. Yeah, I think that's it. Okay, yeah, but I'll give you guys this, and of course if you have any questions about anything, just let me know. But I think everything's there. I think I have all the dates right. Okay. So, yeah, sorry about yesterday. Well, I mean, not yesterday, but Monday. So I was in California, and I was giving a talk over at a couple of companies, Anton Park and also Park Systems. And yeah, so I mean, they went okay. Well, okay, so here's the reason for the talk. And you're like, well, why is the instructor missing class? You know, well, it's really important because Park Systems was a company that started the nanotechnology revolution. Okay, so back in 1986, they figured out a way to image atoms. So before that, no one knew how to do that. So it's kind of weird how they image atoms. So does anyone remember the phonograph record from a long time ago? Maybe your parents, grandparents? The phonograph record. So basically it was a vinyl record, and it had like a little needle you put on the record, and basically it was a cantilever beam, like a diving board. And the diving board had like a little tiny needle. And then it would go into the groove of the record, and in that groove it had different kind of sinusoids. And those sinusoids would represent the music. And then it would, vibrate up and down, and then it would sense that signal and go through op amps, what we're going to talk about today. And then you would hear the sound. Well, these guys took that idea, and they took that needle and they reduced it in size down by a factor of 1,000,000. So it's 1,000,000 times smaller. The needle is 1,000,000 times smaller. So like the radius of curvature of that needle was about 5 nanometers. And 5 nanometers is like the diameter of like 50 atoms across. So it's really, really small. Well, atoms are too small for us to see, right? Because the wavelength of light, the wavelength of the smallest light, like blue light, is about 200 or 400 nanometers. right? So 400 nanometers, and atoms are like 0.1 nanometer, right? So you can't see atoms using wave-light. So, but with this little tiny needle, if you have a scan across the surface, it would sense the hills and valleys caused by the atoms there. And so that's how, and you're just able to, you just raster scan across the surface, and then you come up with this image of the atoms. So the problem that they've been having since the 1980s is that they've been able to image these things, but they haven't been able to measure the forces, right? When it comes into contact, forces between biological molecules. So I came up with a way to measure very small forces, and these forces are like the size of piconewtons. So to give you an idea of what a piconewton is, a newton, like what weighs what weighs 1 newton?
1/10 of a kilogram.
like what object? Huh?
An apple?
Yeah, an apple. Get it?
Oh.
Well, it turns out it's like a medium-sized apple. Okay. So, because apple comes in different sizes. Yeah. So an apple weighs about a newton, and if you take that apple and you chop it up into 1 trillion pieces, 1 trillion equal pieces, one of those pieces weighs a piconewton. Okay, so we're talking about really, really small forces. And like this laser pointer, the photons are hitting that wall and they're having photon recoil and bouncing off, and you guys can see it. Well, that pressure that this laser light has on that screen, it is about a piconewton. Okay, so it's really, really small forces. So anyways, so I figured out a way to measure these forces really accurately. So I'm trying to get these guys to use this technology for their atomic force microscope. So anyways, that's why I was there giving the talks. But anyway, that's the reason why. Well, the most important thing is like, why is that important? Like, why is it important for us to measure like really small forces? Because, for example, like understanding our DNA and protein folding, right? You see pictures of DNA, right? And they have the AT and GC bonds. If you took the strands of DNA and you unzipped it, to break an AT bond, it takes about 15 piconewtons. To break a GC bond is about 10 piconewtons, right? So and that's all there is in DNA, GC, AT, just a sequence of those, and that's called your DNA sequence. If you unzip those things, you could actually do DNA sequencing if you can measure the forces. Right now, to do DNA sequencing, you have to chop it up, you have to have a large enough sample, you have to replicate your DNA, and it takes a really long time. We're talking days and days to do DNA sequencing. But it'd be nice one day if someone could just go to a crime scene, because all these skin cells are dropping off of us everywhere we go, right? I mean, there's a trail of skin cells for each and every one of you from where you live to here that you left this morning, like breadcrumbs. And if they go to a crime scene, they could just, examine skin cells and do DNA sequencing right there in the spot. If they can do, this kind of thing. But anyways, that's just one, example. But there's many things why we need to measure those things. Okay, so here's a little bit about me. Here's my email address. Email me any questions anytime. Okay. Now I'll give you my office hours too. My education, the kind of research I do, not just small forces, but I do stuff in robotics. The thing I was talking about is called metrology and calibration. I do stuff in performance control, computer aided design, AI, and engineering education, and some things on scholarship. Some different kinds of my research right here that I'm doing, like performance control stuff and robotics. These things are making it like they're about the size of an ant, and they're using piezoelectric kind of flexures to move about. Here's a software tool I made. It's all in MATLAB. So here's the course, here are the prerequisites, okay? I've only had this course, where I taught that. I haven't taught that course yet. And I haven't taught this course yet, or taken this course. So I'm actually learning it as we're going. So confine your questions to like the topic at hand. Right? Don't ask me what's the next chapter, because I don't even know yet. So like even today's lecture, I just made it, last night. So and I read, So I'm reading the same book you guys are using. This is this right here by Yeager. It's the 5th edition, not the 4th. And for the grading, here's what I typically do. And those of you who had my class before, I take the maximum of these two scenarios. Either the average of your 3 exams minus any missing homework you do, or the final exam, whichever is greatest. Okay? And so for homework, this piece right here, this homework, so you don't get any points for doing homework, but you do get points taken off if you don't do the homework. Okay? So basically, this part right here should be 0. Right? You should have no missing homework. And then we'll just, your grade is just based on the 3 exams. Now, typically you might be thinking, most classes, they gave us points for doing homework. Yeah, that's fine. But if you think about it, what you're really being graded on is your exams anyway, right? Because 90% of your grade is your exam. Okay? And also you guys can work together on your homework. And also, I tried one thing last semester, in the summer that kind of worked out well, where the homework was multiple choice, and you enter your answers online, and you're able to resubmit your answers online if you get it wrong, without penalty. Okay, so that allows you. That solves this one problem with homework, where, and you've seen this. You guys dealt with this before, where you do your homework, you turn it in, you have no idea if you got it right or not, and then you go to the next lecture and you're on to a different topic. Meanwhile, you have no idea if what you thought about the last concepts were right or not until you get your homework back, maybe a week later. Okay? So this way, you find out right then and there if you're on the right track or not, and so you can make some course corrections and master the material before the next lecture. Okay? So are there any questions about this grading method? Yeah.
How is this functionally any different than just giving points for homework? If you lose points that you already had doing the homework or not doing it, it's no different, right?
Well, it's slightly different. Okay, so yeah, if you do homework, like if you receive points for homework, right? And let's say they typically do like maybe 10% of your grade is homework, 90% is based on exam score. And what I've typically seen, and probably you guys have too, is that people do really well on their homework grade. They get nearly 10, that 10%. And then when it comes to their exam, which is really measuring your mastery of your skill, because homework doesn't really it doesn't measure the mastery of your skill, right? You're able to call your friend up, say, hey, what'd you get for problem 6? You can come see me, and I can tell you how to do it, right? You can see the TA, you can see, you guys can work together. So homework is just practice. The only reason why anyone ever gives you points for homework is just to motivate you to practice. That's the only reason why. So I'm motivating you by taking points away. And that's a stronger motivator. Believe me, that's a way stronger motivator than giving you points for it. Because think about it. But who in this class would not, it's multiple choice. You get the answers right then and there when you turn it, when you enter it, and you find out if it's right or wrong, and you get to do it again. Even if you guessed, you get full credit. So, but what I'm really testing you guys on, to do a really fair analysis, is I'm really testing if you have learned the material. And I can only do that on an exam, right? Where you don't have any help, and it's just you, your pencil, you know, and and a piece of paper. And for those of you who haven't had my class before, you don't really have to worry too much about this, because every time I've done this, my classes, I mean, like, well over, yes, around 80% of the people get A's, you know? Because, you know, how we do things in this class, like, for example, when I make the exams, they are a reflection of the homework, right? And since you know most of your, well, all of your grade depends on the exams, you put more emphasis into doing them. And also there's another benefit. Like I said before, you can either do this method or this method, right? And anyone knows how hard a final exam is, because it's like a 3-hour exam where you're taking like 3 midterms all together. I mean, that's really, you know, excruciating. So if you can master the material early, you can skip the final. And you can concentrate your time in your classes that do have finals. So that's another motivator. And that could be a reason why you know, a lot of people get, you know, good grades. Okay, what else?
Will you be posting on Canvas for this class? Or?
Oh yeah, I'm going to put all lectures on campus. Yeah, on campus. Awesome. Yeah, I'll try to do it before class. So if you guys want to like print it out and annotate your notes, you can do that. Because like when I talk, not everything it happens, you know, is going to appear on the slides. Yeah. Anything else? Yeah.
So how many points, like, would the FBA don't do the homework, would that take away?
Oh yeah. So for every homework that's missed, it's like 1 percentage point of your score. So for example, if let's say your average exam score was 90 and you missed one homework, you would get an 89. And then of course you would get a B. Or the other way, let's say you did 100% in your exams and you missed 10 homework problems, or 11, then you would get an 89. You see? So yeah, so you don't want to miss your homework. And again, it's just to give you your practice. But of course, if you don't like this plan right here, and you think you can just handle the final exam, you know, you just go for it. But typically what happens is that people take the final exam if somewhere in here they messed up for some reason. They had a bad exam day. It happens, right? They're sitting at a B, and they're like, wow, you know, I was so close to an A if I just didn't make that silly mistake. Then what they do, they come back for the final just to see if they can get that A. Yeah. Anything else? Yes?
Isn't that the same book we have for Digitron? Or not?
I have no idea. Yes.
It is.
It is?
Yeah.
Okay. Cool. Yeah, I haven't had Digitron before. So is Digitron like the first few chapters of the book, like the first 9 chapters? Okay. Yeah. So I talked to the author. The author is actually a professor here, Jaeger, and I talked to him. He says, "Oh, you guys are starting on chapter 10." I'm like, what? So please, no questions about Digitron. Not until I teach it, which may be, I don't know, sometime next year. I don't know. All right. So another thing I want to talk about is memory retention, because this is really important for anything you guys are studying, anything you guys are trying to learn. So what these 2 plots are, this is your memory over time without reviewing. Okay. So here's like the percentage of retention, like 100% up here. Here's where you're acquiring new knowledge. Like this class, we're in here for 50 minutes, you're gonna acquire new knowledge, right? So immediately after I repeat something, after I say something to you, you guys can recite it, almost verbatimly, and you would get it right. But then after time, your memory starts to decay. 20 minutes later, an hour later, a day later, 6 days later, and it's pretty exponential decay, as you guys can see. Now, this is what happens if you guys review, okay? So this first plot right here, this first exponential, that is above. That's this one. okay? And if you didn't review on day one, like a day later, it would just keep on fading away like this. So just think about this. Tomorrow, at this time, you guys would have only remembered like maybe 52%, 53% of what I said today. It's biological, okay? Now, maybe some of you are like a little better, a little worse, but that's like average, right? However, if you guys review tomorrow, the notes, or whatever, immediately go back up here, and then you would be on this new decay path, which, a couple days after that, you see that, look, just from one review, 3 days later, it's even higher than waiting a day. And then if you review on day 3, it goes up, and then you follow this path if you never review again. Okay? But if on day 10 you review, you go like this. And actually, you can see this pattern here. So this is like 1, 2, 3, 4, 5. If you review 5 times, it's going to decay so high in asymptote to above 90%. Think about that. Just review your material 5 times and you retain that information. 90% of it. Over 90% of it. Which is very useful for exams, because right before the exam, you don't have to cram any longer. You know the material. And that's really, what idealistically what you guys should strive for, not having to cram before any of your exams. The only reason you cram is because you covered lecture 1, lecture 2, and then you never went back to it. And then you kept on looking at your new stuff, and you never reviewed your old stuff. But if you review your old stuff, you see what happens to your brain. Okay? We don't have a manual to how our brain works, but you guys should try to, figure it out. Because if you do, then you can, take advantage of it, of how your brain works to get the most out of it. Okay. Any questions about the review kind of thing here? It's really important for you guys. Don't underestimate this slide here. It makes a really big difference in your life. Okay, so with that said, for successful acquisition of new knowledge, try not to let me go to a new concept without fully understanding, the last concept that we're on. So when you guys leave the class, try to have everything understood. Don't say like, okay, after class, I'm going to try to figure out what he said. What he really meant. Try to get that understood right then and there. That's the first step, because then all you have left is just review, because you've learned the material. Immediately ask about anything that's unclear. For successful mastery and working knowledge, practice working on problems like the homework, do reflection, and actually use it. Think about creating things. Or when you see a device, try to think about how it's working. It's going to have op-amps in it. And then for successful learning versus rote memory, it's very important to understand why. That's the difference between someone who has actually learned the material and someone who could just repeat something just because they have memorized an equation, but they don't truly understand the equation. They don't understand what it means. This is more important, understanding, because if you understand it, you can use that equation different ways for different things. If you're only going by rote memory, then you have to have a problem exactly like that to use your equation. Okay, so understand why. Okay, so here's a review of what we went over last time. What Ying-san went over with you guys right here. And so operational amplifier, it originates from their function in old analog computers. So they did operations, okay, like summation, integration, differentiation, scaling, etc. And op amps are used to increase or decrease, voltage, current, or power, and that could also can be used for filtering. I think he went over this with you guys about a radio receiver. Wait, did he go over this stuff with you guys? Mm-hmm. Okay, cool. Yeah, so op amps are all throughout this stuff right here. Taking, doing your impedance match from this antenna coming in, impedance matching for your speakers going out, all the processing that goes on inside. And now this right here this is kind of complicated if we have all the components, but you can model it like this, right? Where here's like the antenna, and the antenna has some resistance, and here's your amplifier, your receiver, and here's the speaker over here. And this part in here can be abstracted to be like this, where as seen from the outside, this whole amplifier looks like it has a resistance of this Rn, right? And then from this side over here, it looks like the amplifier has a resistance of R out and some voltage, which is amplified right here. Okay, so this is something that is used to really abstract lots of things here. And of course, from that, I think you guys covered gain, right? So gain is just output over input, so gain of the voltage, magnitude and phase. Current gain, output over input, magnitude and phase. And here's the power. So it's RMS of the voltage and current. Okay. You guys know what RMS stands for? Yeah. Mathematically, do you know what it means? Huh?
Square of the root.
That's for a sinusoid. If it's, this is important. So if it's something else like a square wave, it's not going to be over square root of 2. Okay? If it's, other shapes, okay? So, but what that means is, so root means squared. What that means is, think about it like this. RMS. The root, right? The mean, you know how to do average. If it's the integral, the average like this of, whatever your function is, right? That's how you do average. And square is, whatever your thing is, let's say it's voltage, you're in your square again, okay? This could be anything, and if it's a sinusoid, 1 over square root of 2 is going to be the factor. If it's some other function, if it's noise or something else, you put it here, you square it, and you do root, mean, and square. And then that's how you get the value. Okay? That's RMS. And also decibels. Did you guys go over this too? The decibel thing? Yeah, so a couple of things to point out. So here's the gain amount. This is the number that makes most sense to us, right? Because that's the ratio. If it's 100 times greater, it's 1,000 times greater, that's the ratio. This right here is for the voltage or the current, and this is for the power in decibels. Now, as you can see, if output and input are equal, the ratio is 1, right? But here's 0 decibels. Did you guys talk about why these decibels are different than these decibels?
Yeah.
Okay. But did you guys talk about why they're equal to this, regardless? Huh?
I don't think so.
Okay. Okay. So let's do power. Okay. So so for power, we know that is 10 log of base 10 of for power we do something like this: the output over the input. Okay. Now, of course, the resistances are going to cancel. So this is 10 log V squared output over V squared input, right? And this part on the inside, you can just write it like this. Factor the power out, and then that you could just take this 2, put it outside, and then you have it like this. Right? So look at that. We came from this, which is power. Power is squared. Some signal that's been squared is power. To this, where the ratio is not squared. But that's the ratio of the amplitude of the gain for just voltage. Right? Because remember, the gain for voltage is just V out over V in. So if you think about it, if you're looking at voltage only, you use this, 20 log V out over V in. If you're looking at power, you're going to use this kind of thing where it's 10 log this over that, okay? But it's squared. And that's the reason why this has a 20 and that has a 10. It's only because they took the 2 out. That's it. They're equivalent though. That's why both of these, if you're going to look at the voltage, is 60 dB, well that's a gain of 1,000. If you do it in terms of power, it's only 30 dB, but it's still 1,000. Because, you know, the equal thing sign is there. You know, I didn't change anything. Okay? So yeah, so that's the reason why for that. And of course, I think you guys went over the 2-port, right? Sort of simplifies the behavior of things. There's other things. There's like so this right here are the G parameters. Okay, so if your equation looks like this, or that's what you're interested in, you put it in matrix form too. Okay, where that's the current at this port here, that node 1, and voltage at node 2, and you have your G parameters, and it's for that voltage and current. But you also have the Y parameters, you have the Z parameters, you have the H parameters. And the only thing that really changes is what your dependencies are. Like, let's say these are the things that you're interested in. So those are your outputs of this function, whatever you want. And these are the inputs. Okay? So you look at the kind of output you want and kind of input you're dealing with, and now determine which kind of parameter scheme you're going to use. In the book, they generally use this scheme right here. So they're mostly interested in I1 and D2. Okay, and it's called a 2-port because you have 2 ports here, the input and output, typically. Okay. So the new concepts. So we're going to get into operation amplifiers, distortion amplifiers, differential amplifier model, ideal differential and operational amplifiers, and analysis of circuits containing ideal. Okay, so here's a typical picture of an op-amp. Okay, an op-amp is a very high performance differential amplifier, or these are called difference amplifiers. So we're going to cover these difference amplifiers first, and then we'll talk about the operational amplifier. Okay, so a difference amplifier is a circuit element that amplifies the difference between 2 input signals. So like these 2 right here. Okay, now this amplifier, it has voltage supply, and typically they're symmetric. Sometimes they're not, but typically they're symmetric. And this output voltage for this difference amplifier is in between these values. So if you're putting like negative 5 volts here, positive 5 volts there, then this output can only go as low as negative 5 volts, and it can only go as high as positive 5 volts. That's it. Okay. And also, when you guys see these pictures and circuits, typically they leave off the power supply part. Okay, so these part will be covered up, and all you see is those. And if the schematic is really lazy, all you see is one input coming in, and that's it. You guys probably see those too. Yeah, but that's what this thing looks like. Now, let's look at the voltage transfer characteristic. So this is a plot, and it plots the output voltage versus this VID right here across the inverting and non-inverting nodes. Okay, and this is typically what it looks like in the idealistic kind of sense, where this is quite linear. In real life, it's not super linear, but we're approximating here. Okay, here's a little offset right there, but then it saturates, because like I was saying before, this can only go as high as VCC and as low as VEE. Okay. Now, this VID can be described by a DC component and a signal. Sometimes this is sinusoidal. Well, most of the time it's sinusoidal. And it's like a small signal, small amplitude. Okay? And this V out can be described by this DC term plus, its signal. that's on top of that. Okay, and typically those DC voltages here and here, they're used to like tune it so your operation is somewhere along this piece right here. Okay, so you have your linear operation of your amplifier, and it doesn't saturate and distort. But sometimes you want that. You know, so I mean, if you're like making a fuzz box for a guitar, you know, you'd want, you know, some distortion in there and do other things. Okay, so now for voltage gain of amplifier, it's based on the slope of any particular point right here. Okay. Now these non-inverting amplifiers have a positive slope, so they are in phase, right? But the inverting amplifiers have a negative slope, so they are 180 degrees out of phase. And that's just a sign change. Okay. Now this part right here, this is the offset voltage. Okay? And that's what's required to force the output voltage, you know, to be 0 volts. Okay, so at that voltage, that offset voltage, this thing crosses the line at 0 volts for output. Now, let's look at signal amplification. So think of this as some input signal coming in, right? It has a DC component, right? And it has some other signal that you're really interested in, right here. In this case, it's a sinusoid. Now, this is what's coming in for this VID here, for the input. And once it goes through here, it comes out like this. So the output looks like this, where the DC component was amplified to 5, and this piece right here was amplified to this amount right here. Okay? So now let's look what happens if this piece right here was like, I don't know, like a little larger, like the amplified, like the amplitude was a little larger. What would happen is this piece right here would go and get on to this piece right here. And so you would have some clipping, and that's what it shows here. So, so here's like 2 input signals. So you have this input signal here, VID1, and another input signal right here, VID2. This is a very small amplitude sinusoid right here. Okay, when you send this through, it comes out with V output 1 like this. Okay, no clipping. But if you send this signal through, which has a higher amplitude, in this particular case, it comes out with this output, where it gets a clip, at least on this part right here. Not below, but in that part it gets a clip. Okay? And that's how you get your distortion and higher harmonics. Okay? Let's look at distortion now. So, so a measure of distortion is called the total harmonic distortion, THD. And so this, which compares the undesired harmonic content of the signal to the desired, this should be content, component. So if you look at a Fourier series representation of the distorted output, it looks like this. You have a DC term, right, that raises or lowers the signal. You have the desired output, which is at the same frequency as the input, but then you can have some harmonics. The second harmonic, which is twice omega. The third harmonic, which is 3 times omega, and so on. These are the things you don't want, right here. So it's also often expressed as a percent THD, and it's given like this. So it's like you're summing up all of these squared. So from V2 on, you're squaring all of those from 2 to however how many you want to go, and divide it by this one right here, the amplitude of that. And that's your total harmonic distortion. And if your THD is less than 1%, that's typically very good. Okay, so so the differential amplifier model. So we'll go over this. It didn't go into the ideal. Okay, so it's a 2-port representation. Here's your input port, right? Your voltage and current input. Your output's over here. So a 2-port system. Okay, so this A right here is your open circuit voltage. That's what that is. This VID is the difference between this voltage and that voltage. RID is the amplifier input resistance right here, and RO is the amplifier output resistance right there. So that's what anything out here sees this resistance. Anything over here sees this resistance. Okay. Now let's look at the impact of the source and load. So I put the source in red. So you've attached some kind of source onto this. So you have some supply, and this resistance is like all the lumped resistance of your source. That's how that's being represented. And let's say it's attached to a speaker or something else you're driving, and you can, abstract that to some type of load. Okay, and that's in blue here. Okay, so your voltage, your VID right here is, if you do voltage division, that's this voltage right here multiplied by this fraction, which is this resistance right here, the RID, divided by both of these added together, the total resistance. And the output voltage over here, that's of course this input voltage right here times this over the sum right here. And the gain is just these two right here. So, I'm sorry, not these two, but this one divided by that one, the input. Okay, that's what you get right here. Okay, so for ideal amplifier, so an ideal differential amplifier produces an output that only depends on VID and is independent of RL or RS. So it's independent of these two guys right here. Okay, so this can be done by assuming RID is infinite and RO right here goes to 0. So if you did that in these equations, if this was infinite, this becomes really negligible, and so this fraction right here becomes 1. So that's why this VID just becomes S. And for this right here, if this RO goes to 0, then no matter what this is, it becomes 1, and so this just becomes that right there. And so what happens is that your amplitude, your gain of your voltage, is just A, because both of these quantities are 1. Okay, so for an ideal amplifier, it's just like an ideal differential amplifier that has infinite voltage gain right here. Okay, and this can be done by assuming this, that RID here goes to infinity. Okay, R0 goes to 0, and A is infinity. So what happens is that this right here, so if A goes to infinity, this fraction goes to 0, and if RID goes to infinity right here, then that means that you're not going to have any current going in here or out of there. Okay, so here are the two assumptions for an ideal op amp. It has more assumptions, but here are the big ones. Okay. Typically, you're mostly just concerned with this right here. So on an op amp, the voltage here equals the voltage there, and the current here, no current comes in or out, no current comes in or out, because you're assuming that this resistance is infinite. Okay. So here is the basic setup for an inverting op amp. Pretty much looks like this. So the positive input is typically grounded, not always, but it's typically grounded. The feedback network is formed by the resistors R1 and R2 right here, and it's connected between the inverting input and the signal source and the inverting input and the amplifier. So between here and here and here and there. Okay. And so if we were to analyze this, if this is grounded right here, that means that has 0 volts. And if that has 0 volts, then that has 0 volts. Okay? So if I had a voltage source right here, this was 10 volts, then what would this be right here? Yep, 10 volts. Okay? Now, if you're trying to find out what this input current is, what you have to do is look at the voltage here and the voltage here and just do Ohm's law. Right? So, in this case, if that's 0 volts, that's 0 volts. It's sort of constrained to be 0 volts. So if that's 0 and that's, I don't know, 10 volts, then you can find current by looking at V equals IR, or I equals V over R. That will determine what that current is. And if that current is that going through this resistor, and there's no current going through here, what happens to this current? All of it goes around here. The entire current, whatever is coming through here is being forced through here. It can't go this way, so all of it is pushed around in here. So this current I2, it equals this current. Okay? And then that allows you to determine what this voltage must be as it goes through this resistor. Okay? Because again, you know what this voltage is, you know what the current is, and so you find out what the voltage drop is, and then you say, okay, whatever voltage is here, minus that voltage drop, that is the voltage that I get at that point right there. Okay, so op amps are kind of weird. I mean, these ideal op amps, nothing in real life is truly ideal, including these op amps, but they make a really good approximation, and they're really easy to analyze. Okay. Now another thing I want to mention. So this voltage totally depends on how much current is being passed through here. If this current increases, that changes this voltage. Okay. Also, what about this current right here? We didn't talk about that yet. Are there any constraints on this current?
Input supply.
Huh?
Input supply.
The input supply? No. Nope, it's not controlled by that. Because remember, here's our two assumptions about the op amp. You know, we have a constraint right here with these currents right here. And of course, this voltage is constrained to be whatever we say it is with this current going through, but we have no constraint on that current. That current, I0, it could be anything. It can even be going into the op amp, this direction. See all these directions right here? Are they important? You guys? Huh? You might want to guess?
No.
So you're saying no?
They dictate the size.
Yes. Yeah. Well, that's why they're important. For that reason. So if someone says, oh, my current is 5 amps, is that enough information for you? If someone just says, oh, it's 5 amps, you don't know what direction it's going. And here's the reason why the direction is important. Because if this current of 5 amps is going this direction, this voltage is high, this voltage is low, voltage is going downhill in this direction. If I have 5 amps, if this was negative 5 amps, you look at the arrow and say, oh, my current's going the other direction. And if your current's going the other direction, that means that this side here is higher by 5 volts than that side. So it's going downhill that direction. Okay? So my time's up. I'll post this online on Canvas, and I'll also post a homework on Canvas as well. All right, so I see you guys on Friday.